In the past, gas engine fuel injection was reserved for ultra-expensive sports cars and, well, cars that were driven only a quarter of a mile at a time. They were mechanical fuel injection systems, and they just weren't very practical for the demands of reliable, everyday road transportation. But modern electronic technology has changed all that. Welcome to today's world of electronic fuel injection. EFI is increasingly becoming the fuel system of choice for automotive gas engine application. Modern EFI systems are more reliable than the old mechanical fuel injection systems and offer fuel economy advantages over carbureted fuel systems. They also offer improved drivability for vehicle owners. In today's world, electronic fuel systems are playing an ever-increasing role.
That's right. Carburetors are mechanical fuel metering devices and don't offer the fuel economy savings that EFI systems do because of their design limitations. Electronic fuel injection systems can adapt themselves to most driving situations while providing top fuel efficiency and optimum engine performance. But unless you know how EFI operates, all those electronics can be intimidating.
Today, in the first of two programs on the basics of fuel injection, we'll give you an overview of how EFI systems work. We'll discuss some of the components of electronic fuel injection systems and talk about the information the system collects from the engine. Then, next month, we'll show you how that information is processed and used by the system and tell you about the different modes of operation.
Now, these are the 5 systems you'll encounter most frequently as a Jeep Eagle service technician. There's the Bendix throttle body injection system, found on 1.4-liter 49-state Renault engines built from 1983 to 1985. The Renix TBI system, found on some 1.4-liter Renault engines, on 1.7 and 2-liter Renault engines, and on 2.5-liter Jeep and Eagle engines. The Bosch simultaneous multi-point injection system is found on some California model 1.4-liter Renault engines and on the 1.6-liter turbo and some early 2.2-liter Renault engines. You'll find the Renix simultaneous double-fire multi-point fuel injection system on some later 2.2-liter Renault engines and on 3-liter Eagle engines. And the Renix sequential multi-point injection system is in service on 4-liter Jeep engines.
Of the 5 systems we've listed, there are 2 basic types of systems you'll encounter. The first, most basic type, is called throttle body injection. The throttle body looks a lot like a carburetor, but meters fuel electronically instead of mechanically. The throttle body injection systems we're covering today use one central injector located over the throttle body assembly. The Bendix and Renix TBI systems use a single injector to meter fuel through a throttle plate into the intake manifold plenum. The intake manifold runners distribute fuel mixtures to the individual cylinders.
That's right, Mark. But there's an even more efficient way to deliver fuel to the cylinders. It's called multi-point injection, and unlike TBI systems, it uses a separate injector for each cylinder. On MPI systems, the only thing that comes through the throttle plate is air, and the injectors are mounted near each intake port of the cylinder head. Now, these injectors mix fuel with the incoming air just before it reaches the cylinder, providing an optimum air-fuel mixture. MPI injector nozzles seal and unseal the fuel flow to the intake manifold. The valve is held against its seat by a spring. An electronic solenoid winding is energized by the electronic control unit, or ECU for short. That's a kind of brain for the engine, and we'll cover it later. The ECU activates a movable solenoid armature. This pulls the armature back, lifting the nozzle from its seat. The fuel channel opens, and pressurized fuel sprays into the intake manifold. The fuel mixture is then drawn on the intake stroke into the combustion chamber. Now, note that the single injector on TBI systems is activated in the same way, but that the fuel is distributed to the cylinders differently.
Of the 3 MPI systems we're covering, each system is activated at a different point during engine operation. On certain 1.4 and 2.2-liter engines, as well as on the 1.6-liter turbo Renault engines, the Bosch MPI system activates all the injectors simultaneously for every crankshaft revolution on command from the ECU. This is also true for the Renix simultaneous double-fire MPI system found on some 2.2-liter Renault and on 3-liter Eagle engines. However, only half the fuel required is supplied at that time. The other half is supplied on the next revolution, and the cylinder that's on its intake stroke then gets the necessary amount of fuel. The air-fuel mixture is waiting in the intake manifold at the port until the opening intake valve draws the mixture into the cylinder.
And you can bet it doesn't wait long either. Now here's something else you should know too. The Bosch simultaneous MPI system also features a 5th cold start injector. This injector sprays fuel directly into the manifold during cold engine cranking only for easier starting. We'll talk more about this in next month's program.
Then there's the Renix sequential MPI system found on the 4-liter Jeep engine. The injectors are activated individually for each cylinder, and the system uses precise timing to send the mixture just when the cylinder needs it. Well, Bob, you think they're catching on?
Let's bounce some fuel injection terms off them before we decide that. Toss open loop at them.
Sure. The fuel injection system operates in open loop mode when input isn't being sent from selected engine monitoring components, usually the oxygen sensor. The open loop mode is activated during cold starts, engine warm-ups, and wide open throttle operations. By temporarily locking out the oxygen sensor input, the ECU is able to satisfy the fuel requirements for all those operating conditions. This helps the engine start when it's cold, promotes reliable warm-ups, and optimizes wide open throttle acceleration.
And it naturally follows that there be a closed loop mode. During closed loop operation, the ECU is accepting information from all operating detection system inputs. We'll fill you in on those shortly. Closed loop operation optimizes air and fuel mixture ratios based on oxygen sensor input to reach the ideal stoichiometric level, 14.7 parts air to 1 part fuel.
How about pulse width?
Lay it on 'em.
Pulse width is the duration the injector nozzles are held open by the ECU. The pulse width is determined by engine speed. This information is modified by other information from the detection system inputs fed into the ECU. This input includes information on airflow, temperature, and manifold absolute pressure, the engine coolant temperature, throttle position, air-fuel ratio, and battery voltage levels. The ECU processes this information and sends time duration pulses of different widths to the injectors. This determines the length of each injection.
We've been doing a lot of talking about the ECU. Let's make sure everyone knows its function. The electronic control unit receives information from a number of inputs which monitor engine operating conditions. It analyzes the data it gets from those inputs to determine the engine's fuel needs. On most systems, it controls ignition timing. The ECU also makes adjustments to various fuel injection support systems. It's wired to the detection system through 1 or 2 wiring harnesses and is usually mounted under the dash or inside a kick panel. The ECU is called the control system. Now let's talk about the fuel system. It consists of the fuel tank, fuel pump and filters, and the fuel pressure regulator. Since everyone knows the fuel tank holds the fuel supply, let's move on to the pump. On all 5 systems, it's an electric rotor cell pump. All but a few of the Bosch MPI system pumps are mounted inside the fuel tank. The other Bosch MPI pumps are mounted to the chassis outside the tank, where they pull fuel from the tank and then push it through the lines. On the in-tank pumps, fuel flows around the electric motor and through 5 roller chambers. A sock filter at the pump inlet keeps contaminants out, and a check valve at the outlet and internal pressure relief valve are integral features of the pump. On the outlet side of the fuel pump, an inline fuel filter is mounted to the chassis near the fuel tank. It separates contaminants from the fuel and is constructed to withstand the higher pumping pressures of fuel injection systems. Farther downstream, on the intake manifold side of the engine, is the fuel pressure regulator. The fuel pressure regulator is calibrated to maintain a preset pressure differential between the fuel line, or rail, and engine vacuum. TBI systems discussed here have an integral regulator built onto the throttle body. It maintains a constant pressure drop across the injector. Now, MPI system regulators are connected to the fuel rail and to an intake manifold vacuum source. Both types of regulators are an overflow type, and based on engine vacuum levels, return fuel, which would cause excess pressure at the injectors, back to the fuel tank through the return line. On MPI systems, this action ensures that fuel pressure is held constant across all injectors under all load conditions. Under high vacuum conditions, such as at idle, during deceleration, and when cruising steadily, the regulator routes more fuel back to the fuel tank. When engine demands increase, the resulting drop in vacuum causes the regulator to divert less fuel to the return line and deliver more to the injectors. Low vacuum levels occur most frequently at wide open throttle or when engine loads increase. As we said before, the fuel pressure regulator maintains a constant pressure drop across the injector or injectors. Now remember, this is a mechanical device and operates independently of the electronic control unit.
I think they're keeping up with us.
Well, me too. Why don't you explain the function of the detection system and show them the inputs?
Here's where the electronics really work wonders. The detection system is made up of inputs, which monitor engine operating conditions. These inputs send data to the ECU for processing and operating adjustments. Because we're covering 5 systems, let's divide the job the detection system does into 6 basic areas. The 6 subsystems the detection system collects information from are airflow, coolant temperature, exhaust gas oxygen content, throttle positions, injector and ignition timing control inputs, and engine accessory load inputs. Some areas, like the coolant temperature and the exhaust gas oxygen inputs, consist of only one component. Others use more than one component to collect all the data the ECU needs. Remember, we're covering 5 fuel injection systems here. And like people, different systems sometimes have different ways of getting the same job done. Bob, how about showing them the airflow inputs first?
All right. Now, you were right about the electronics working wonders, but they just help the engine work smarter, not harder. The airflow inputs, that is, the inputs that monitor airflow or air temperature or barometric pressure, or even all 3, collect data on the air coming into the engine intake to help the ECU determine, in part, the correct air-fuel mixture. Now, we'll start with the manifold absolute pressure sensor, or MAP sensor for short. The MAP sensor measures absolute pressure in the intake manifold and provides input to the ECU. It reads engine load based on intake manifold vacuum to supply mixture density and barometric pressure information to the ECU. This allows the ECU to adjust fuel mixtures to meet altitude and air density fuel requirements for that geographic area. As on all models, the Renix TBI Systems MAP sensor is remote mounted with a tube from the throttle body supplying its input pressure. The manifold pressure varies with engine load and throttle position. It puts out a low voltage signal to the ECU at idle when manifold vacuum is high, and a higher voltage signal when vacuum is low, for a maximum 5-volt output. On this Alliance model, the MAP sensor is located here, on the cowl.
And on Renix sequential MPI systems, the MAP sensor is located here, also on the cowl. Remember though, mounting locations may vary with the vehicle. A MAP sensor system or its equivalent is used on all 5 systems. The next airflow input is the air temperature sensor. It measures the air temperature in the intake manifold and sends a signal to the ECU to compensate for air density changes at higher temperatures. On most systems, when the air-fuel mixture temperature in the manifold is high, the sensor indicates to the ECU that a leaner mixture is required. When the temperature is low, it tells the ECU that a richer mixture is necessary. Sensors on 4-liter Jeep engines with Renex sequential MPI measure only the air temperature rather than the air-fuel mixture temperatures. All types of air temperature sensors are thermistors, and there are two types of thermistors. First, the negative temperature coefficient type, which registers a high resistance at cold temperatures, and at higher temperatures registers a lower resistance to the ECU by sending an analog voltage signal. The other type is the positive temperature coefficient thermistor. It registers a low resistance at cold temperatures and a higher resistance at high temperatures. The air temperature sensor, or its equivalent, is found on all 5 fuel injection systems. The Bosch MPI Systems air temperature sensor is located in the airflow sensor housing, which we'll cover next, rather than in the intake manifold. The simultaneous double-fire Renex MPI Systems air temperature sensor equivalent is mounted on either the throttle body assembly or on the manifold. Remember, you'll find the simultaneous double-fired system on Renault 2.2-liter and Eagle 3-liter engines. And on the Renex sequential MPI system, the air temperature sensor is located on the intake manifold. The sensor on this system is a negative temperature coefficient thermistor.
On Bosch MPI systems only, an airflow sensor is used to measure the volume of air being drawn by the engine. It provides a major input on this system only to the ECU for fuel metering. The Bosch MPI Systems airflow sensor is located between the air cleaner and throttle plate. A spring-loaded flap inside the sensor is moved by incoming air. The flap controls a variable resistor, or potentiometer, which sends a demand signal to the ECU. A compensation flap attached to this main flap smooths flap movement, so input to the ECU is steady. Well, that about does it for airflow components. Let's move on to coolant temperature input.
Hey, I'll take this one. The coolant temperature input measures the operating temperature of the engine and sends a message to the ECU. The ECU needs these signals to know to enrich the air-fuel mixture when the engine is cold and to lean it out as the coolant temperature rises. This is the only component in the coolant temperature input section. You guessed it. It's the coolant temperature sensor. It's a negative temperature coefficient thermistor, which means that at cold temperatures, its resistance is high. As it heats up, its resistance decreases.
Now remember, on this Renex TBI system, the sensor is located in the coolant jacket.
The coolant temperature sensor is located in the engine coolant jacket on all the systems we're covering. The exceptions are the Bosch MPI system, where the sensor is located in the cylinder head or thermostat housing, depending on the vehicle model, and the Renex TBI sensor on Premier, which is located in the thermostat housing. The coolant sensor input is also used to determine warm-up idle speed, add spark advance, and lock out the EGR function when the engine is cold.
Another area of the detection system is the exhaust gas oxygen sensor. It's mounted in either the exhaust manifold or pipe and signals the oxygen content of exhaust gases to the ECU. Rich mixtures have a low exhaust gas oxygen content, and lean mixtures have a high oxygen content. The signal sent by the oxygen sensor helps the ECU analyze the air-fuel mixture ratio. In short, it's a report on how well the fuel mixture is being managed.
In the 5 fuel injection systems we're covering, there are 2 basic types of oxygen sensors. 3 of the 5 systems use a voltage-producing sensor, like the one I'm holding here. This type of sensor sends a voltage to the ECU for analysis. The ECU uses this voltage as a reference and adjusts the air-fuel mixture in accordance with the voltage changes sent by the O2 sensor. Voltage-producing oxygen sensors are used on the Bendix TBI, Renix TBI, except the 2.5-liter Jeep Eagle engine, and Bosch MPI fuel injection systems. The other type of oxygen sensor you'll see in service is a variable resistor type found on 2.5-liter Jeep Eagle engines with Renix TBI and 3-liter Eagle engines with Renix simultaneous double-fire systems. It's also on 4-liter Jeep engines with Renix sequential MPI systems. Instead of the sensor sending a voltage to the ECU sends a 5-volt signal to the sensor. The ECU measures the voltage drop across the resistor sensor by the voltage it sends back. The value of the return voltage signal indicates a rich or lean fuel mixture.
There's also another feature you should know about. Let's see that sensor for a minute, Mark. Now, some oxygen sensors have a heating element in them to bring the sensor up to operating temperature sooner. When a vehicle is started cold, the sensor is cold too. Until the oxygen sensor reaches its operating temperature, the fuel injection system stays in the open loop mode for easy starting and good drivability when the engine's cold. Heating the sensor electrically allows the system to go into a closed loop mode more quickly, with the ECU accepting inputs from all of the detection system sensors a lot sooner. It also allows the system to stay in the closed loop mode during extended engine idling periods. The 2.5-liter Jeep Eagle, 3-liter Eagle, and 4-liter Jeep engines use electrically heated oxygen sensors. All right, Mark, let's take a look at the throttle position inputs now.
Okay. As a group, these components tell the ECU where the driver's holding the accelerator, or if he's pressing down on it at all. This way, the ECU can make adjustments to respond to engine loads. It's done in a variety of ways on the 5 systems, so we'll cover each component and tell you which system it's on. Let's start with the throttle position sensor. It contains a potentiometer, or variable resistor. This lever I'm moving activates the potentiometer, and on the vehicle is operated by the throttle plate. The potentiometer varies the signal to the ECU, depending on the throttle plate position. This input allows the ECU to determine the throttle position accurately under all driving conditions.
The throttle position sensor is located on the throttle body assembly on this Renix TBI system. You'll find a throttle position sensor, or TPS, on 2.5-liter Renix TBI systems, as well as on Renix simultaneous double-fire and sequential MPI systems.
On vehicles equipped with either Renix MPI system and an automatic transmission, you'll find a dual throttle position sensor assembly. On this 4-liter Renix sequential MPI system, the dual TPS system is located right here on the throttle body assembly. This extra TPS on the Renix system informs the automatic transmission of the throttle position, so it can make the right upshift or downshift under all driving conditions. The 2.2 and turbo 1.6-liter Bosch MPI systems also feature an automatic transmission TPS. However, it's a different type than the one used for engine operation. We'll cover the engine operation type a little later. Now, let's talk about the TPS on the Bendix TBI and the 1.4 and 1.7-liter Renix TBI systems. Models equipped with these systems and an automatic transmission feature one TPS for the automatic transmission only. In this case, the actual fuel injection system doesn't use one. The transmission ECU uses that TPS information to schedule transmission shifts. Vehicles with manual transmissions don't need an additional TPS for this purpose.
Now we'll talk about the closed throttle switch found on the Bendix and Renix TBI systems. This switch is located on the side of the throttle body and is an integral part of the idle speed control motor, an ECU output that we'll cover next month. The closed throttle switch provides the ECU with a digital voltage signal to indicate a closed throttle condition, such as at idle or during deceleration.
And at the other end of the spectrum, there's the wide-open throttle switch. It's also found only on the Bendix TBI and the 1.4 and 1.7 liter Renix TBI systems. It's mounted on the side of the throttle body near the closed throttle switch. It's designed to close at 12 to 15 degrees before the wide-open throttle position. That's when it sends a digital voltage signal to the ECU to indicate a wide-open throttle position. The ECU responds to the signal by providing a richer mixture for the increased engine load and goes into open-loop mode.
As always, there's a nonconformist in the group. Unlike the potentiometer TPS on the other systems, the Bosch MPI system uses a single throttle valve switch assembly to inform the ECU of throttle position extremes. It's mounted on the throttle valve housing and contains two sets of contacts, idle and full load, or wide open throttle. These contacts are activated by throttle shaft movement. At idle, or wide open throttle, the switch signals the ECU. The ECU increases injection duration to provide appropriately richer mixtures at these throttle positions. When the idle contacts close during deceleration, the ECU halts fuel injection until engine speed drops to approximately 1,500 RPM. This helps reduce exhaust emissions. Now, when the engine slows to this RPM level, the ECU resumes fuel injection to the cylinders. All Renix systems, except the 89 simultaneous double-fire system, also have a deceleration fuel cutoff feature. Remember, of the 5 systems we're discussing, the throttle valve switch is found only on the 1.4 liter California engines and on the 1.6 liter turbo and 2.2 liter Renault engines with the Bosch MPI system. Mark, I'd like to show them the importance of the injector and ignition timing inputs now. Why don't you tell them a little about it?
Yeah, I think I'll start with the speed sensor. All 5 systems use a magnetic speed sensor mounted on the bell housing to detect engine speed and crankshaft angle. This specially toothed flywheel sets up a magnetic field between the speed sensor and the teeth.
Because the speed sensor is magnetized, it picks up a small induced current each time a tooth passes by. Special trigger notches on the flywheel, the gaps you see on the flywheel here, are positioned to tell the ECU what the engine speed is and piston positions are. A 4-cylinder engine has 2 trigger notches located 180 degrees apart, while the 4-liter Jeep and 3-liter Eagle 6-cylinder engines have 3 notches located 120 degrees apart. The drastic shifting of the magnetic field that occurs every time a trigger notch passes the speed sensor produces a change in the inductive current, which makes its way to the ECU. We'll tell you more on how it gets to the ECU in a minute. The disturbance that occurs in the magnetic field every time a tooth goes by enables the ECU to actually count each tooth on the flywheel. The ECU knows that top dead center comes 12 teeth after the trigger notch, and all 3 Renix system ECUs can adjust ignition timing by counting these teeth. However, the majority of ignition timing decisions on the Bendix TBI and Bosch MPI systems are made by the ignition control unit.
Unlike the 3 Renix systems, the speed sensor signal on the Bendix TBI and Bosch MPI systems is first sent to the ICU instead of directly to the ECU. The ICU on these 2 systems directs the spark curve for the engine. The ECU ignition input is limited to adding 4 to 8 degrees of ignition advance. We'll call it a smart ICU, since it does most of its thinking for itself. These ICUs provide the ECU with engine speed sensor input so it can adjust injector operation to meet engine load demands. Remember, these smart ICUs are featured only on the 1.4 liter Bendix throttle body system and on the Bosch MPI systems, which are found on the 1.4 liter California engines, 1.6 liter turbo, and 2.2-liter Renault engines. You'll most often find them mounted on the cowl of the vehicle, and in some cases on the shock tower. If you're at all in doubt as to its location, just trace the high-tension ignition lead back from the distributor cap. On both systems, it leads back to the ICU. Speaking of ignition timing inputs, knock sensors on the Renix 1.7-liter TBI, the 1988 3-liter Renix simultaneous double-fire system, and the 4-liter Renix sequential systems are able to detect excessive engine vibration associated with engine knock and detonation.
The knock sensor is located on the lower left side of the engine block on Renix sequential MPI systems. It contains a crystal which constantly vibrates and sends a voltage to the ECU while the engine is running. These voltages increase with intensity of the vibrations. The ECU decides from the voltages whether a knock is present and then retards ignition timing by a predetermined value on any single cylinder or combination of cylinders. After a number of engine revolutions without knock, the ECU advances the ignition timing progressively back to its setting prior to the engine knock. The knock sensor is found on the 1.6-liter turbo engine equipped with the Bosch simultaneous MPI system, the 1.7-liter Renix TBI, 3-liter Renix simultaneous double-fire, and on 4-liter Renix sequential MPI systems. The ECU also uses ignition system information to determine when to energize the injector for fuel delivery. Because the engines covered here have more than one cylinder approaching TDC at the same time, the speed sensor is unable to tell the ECU exactly which cylinder is on which stroke of the 4-stroke cycle. And because 4 of the fuel injection systems only need engine speed information to determine injector timing, this information isn't critical. However, on the Renix sequential MPI system, which energizes individual injector nozzles for individual cylinders with precise timing, it's very important.
Renix sequential MPI systems need to know which piston is approaching top dead center on the exhaust stroke. That way, the ECU can energize the correct nozzle for that cylinder. This is accomplished by supplementing the speed sensor with a sync signal generator. I'll take a breather and let Bob tell you how it works.
The sync signal generator, located inside the distributor, works together with the speed sensor. It locates pistons number 1 and number 6 during engine cranking only and uses them as reference points to determine the correct fuel injection nozzle energizing order. The ECU knows what order to fire the injectors in, and once the sync signal generator has determined where cylinders 1 and 6 are, the ECU simply uses the speed sensor input for operation.
The pulse ring rotates inside the distributor. A stationary signal generator sets up a magnetic field, which the pulse ring passes through. This weakens the magnetic field and indicates to the ECU piston number 1's position. When the pulse ring leaves the signal generator, the field information is passed to the ECU, which determines the proper order to energize the injectors. Remember, the sync signal generator is used only on the Jeep 4-liter Renix sequential MPI system.
Whew, that was a mouthful.
Yeah, that's for sure. And now that I've come up for some air, Bob, you can take everyone on to some other areas of the detection system.
All right. To activate all these wonders of modern electronics, all you have to do, turn the key. And when the ignition key is turned, a voltage signal is sent to the ECU on every one of the 5 systems. This signal serves as a wake-up call to the ECU, which then determines when to energize the injector and ignition systems. On the Renix TBI and Renix sequential and simultaneous double-fire MPI systems, the engine crank signal allows the ECU to begin counting flywheel teeth when the starter's engaged, deliver fuel, and energize the ignition system. On the Bosch MPI system, the ECU and power relay receive a tachometer signal from the ignition control unit. This shows that not every input to the ECU comes from an electronic component, At least, not the kind of electronic component you'd think. Mark, how about running the battery voltage signal past them?
This signal is a message to the ECU to adjust the pulse width, remember that term, of the injectors to compensate for voltage variations. If the system couldn't compensate for lower voltages, the injector pulse width would be too short, resulting in overly lean mixtures. This way, the ECU lengthens the injector pulse width. All systems except the Bosch MPI feature a battery voltage signal. Okay, Bob, why don't you grab the wheel now for the accessory load detection inputs.
Fancy names for easy concepts. Okay, now when the driver activates some engine-driven accessories, they can create sudden loads on the engine. These loads can be so great that they'll stall out the engine. The two most common causes are the air conditioning unit and the power steering unit on vehicles equipped with those accessories. Most of the air conditioning units on the Renault and the Jeep vehicles that we're covering can compensate for this condition. And some of the power steering units have a way to keep from stalling out the engine when they're turned hard. Let's start with the air conditioning select signal input. The function of the air conditioning select signal input is simple. It supplies the ECU with a 12-volt signal when the AC switch on the instrument panel is activated by the driver. The ECU then raises the idle speed to compensate for the additional load.
The air conditioning select signal input is found on all systems except the Bosch MPI. On Bendix TBI systems, there are some differences between 1984 and 1985 models. So see your service manual for more information.
Then there's the air conditioning request signal. This input sends a signal to the ECU from the air conditioning temperature control thermostat to indicate that air conditioning is required. The ECU uses this information to determine the required idle speed. On Bendix TBI, Renix TBI, and Renix sequential MPI systems, it also activates or deactivates the AC compressor clutch.
Like the air conditioning select signal input, the request signal is a feature of the Bendix and Renix TBI systems and the Renix simultaneous double fire and sequential MPI systems.
Another accessory load input component is the power steering pressure switch. You'll encounter this switch only on the Renix TBI-equipped 2.5-liter Jeep engines found on XJ and YJ vehicles. It supplies input to the ECU through the air conditioning select and request input lines. When power steering pressure exceeds a predetermined level, for example, during parking maneuvers, the power steering pressure switch closes to inform the ECU to raise idle speed to compensate for the additional load. On vehicles equipped with this feature, the switch is mounted next to the power steering pump.
The next ECU input component on our list is the load swap relay. While it doesn't really qualify as either an ECU input or output, it works with the power steering switch, so we'll cover it here. The load swap relay disengages the air conditioning clutch when power steering unit loads make it necessary. When the driver is operating the air conditioning unit and the power steering pressure switch signals the ECU to increase engine idle speed, the load swap relay removes power to the clutch relay until the power steering pressure switch reopens. You'll find the load swap relay on 1986 Jeep Cherokee, Wagoneer, and Comanche models. The load swap function was incorporated into the ECU in 1987, and the remote-mounted relay was then eliminated. This load swap function eases accessory loads on the engine during low-speed maneuvers and only interrupts air conditioning until power steering loads ease up. There's a built-in half-second delay in re-engaging the AC clutch when the power steering switch reopens to prevent clutch bounce. You'll find the remote-mounted load swap relay only with the power steering pressure switch, since they work as a team, and only on 1986 Renix TBI-equipped 2.5-liter engines found in Jeep Cherokee and Comanche. Don't forget, though, that the load swap function is performed by the ECU on newer models.
The gear indicator signal comes last. It's used only on vehicles equipped with automatic transmissions. It's a switch mounted on the transmission. It informs the ECU when the gear selector's been placed in a driving mode. The ECU then raises the idle speed to compensate for the additional load. Manual transmission equipped models don't need this signal because the driver controls the in-gear throttle application. The gear indicator signal is a feature of the Bendix and Renix TBI systems and the Renix simultaneous double fire and sequential MPI systems.
And that covers all the inputs for the 5 fuel injection systems we're covering today. Modern electronics have given us control over our vehicles' fuel systems like never before.
But that's only half the story. Today we've covered the ECU input half of the system and shown how each input area operates. Before we go, let's list all the electronic inputs to the ECU. They are the MAP sensor, the air temperature sensor, the airflow sensor, the coolant temperature sensor, the oxygen sensor, the throttle position sensor, the closed throttle switch, the wide open throttle switch, the throttle valve switch, the speed sensor, the ignition control unit, the knock sensor, the sync signal generator, the engine crank signal, the battery voltage signal, the air conditioning select signal, the air conditioning request signal, the power steering pressure switch, the load swap relay, and finally, the gear indicator signal.
I wish my grandfather could have seen how far we've come. He'd be amazed.
He sure would. But because of his background on the basics of internal combustion engines, he'd never forget that there's still an engine under all these electronic marvels, and that the electronics are a fantastic means to an end.
Next month, we'll have the rest of the story all revved up for you. It's the other side of the fuel injection basics, the electronic control module outputs, which control the system's operation. We'll also look at fuel injection system modes of operation, which covers all the operating conditions a vehicle sees on the road. We'll see you then.
The VideoTec program this month includes a demonstration of the service procedure for safety recall number 271T involving the windshield frame and wipers of 1987 and 1988 Jeep Wranglers. Before beginning that demonstration, we want to highlight some of the recall procedures used by Chrysler. This should help Jeep Eagle dealers to understand and implement recall service requirements. First, note that all recall instructions are provided to dealers by way of dealer recall notification letters. No separate bulletins are used. The first page of the dealer letter has a wide orange border at the top with the words recall notification for quick identification. The involved dealers, those who sold any of the recalled vehicles, will receive a listing of those vehicles and a copy of the instruction letter at the time of recall notification. Other dealers will not receive vehicle listings, but will receive copies of the instructions by compact mail. The dealer notifications are mailed at about the same time that the parts are available for the repair. For most recalls, an initial shipment of the necessary parts will be delivered to involved dealers about 1 week before owners are notified of the recall. This prepares the dealers in advance so they may provide repairs immediately upon request. Those dealers who did not sell any of the recalled vehicles will not receive an initial parts supply in most cases. These dealers should order parts when needed to perform the recall service. Most recall parts are provided free of charge to dealers. In some cases, dealers will be charged for the parts. The dealer instructions include complete parts distribution and expense details for each service procedure. When owners are notified of a recall, they are asked to contact their selling dealer if it is convenient. Otherwise, they may ask any Jeep Eagle dealer of their choice to perform the service. It's important to note that we have a legal obligation to perform safety and emission recall service. Do not turn any owner away. An owner recall notification form is enclosed with the owner instructions. This is to be delivered to the dealer at the time of service. The form will identify the recall and the vehicle involved. It may be filled out as needed to provide the owner with a record of the recall service completion. This form may also be used to inform Chrysler of a change in the vehicle disposition or owner status. Chrysler records the completion of recall service on vehicles from the claims submitted by dealers on the dial system or on WROs as applicable. Recalls will be detailed in this and future VideoTec programs for your information and action. The service procedure outlined in this program involves a condition on all 1987 and 1988 Jeep Wranglers in which windshield frame cracking may occur. As a result of this condition, the wiper linkage may bind, reducing visibility. To correct the condition, involved vehicles must be fitted with a windshield frame reinforcement and revised wiper linkage. Parts required for this procedure are contained in Recall Parts Package Part number C3940-330. An initial part supply will be shipped free of charge to all involved dealers before owner notification for the service of affected vehicles. Each dealer to whom involved vehicles were invoiced will receive enough parts packages to service 50% of those vehicles. Contents of the package include a windshield frame reinforcement, a wiper linkage pivot body and arm assembly, a linkage drive arm, 2 pivot nuts, and 1 package of epoxy. Additional parts packages may be ordered without charge from your parts depot if required. Before starting the service procedure, inspect the windshield frame for cracking at the driver's side wiper pivot mounting boss. If cracking has already occurred, the windshield frame must be replaced using normal service procedures. Currently, serviced replacement windshield frames already have reinforcements, double metal thickness, at the wiper pivot mounting areas. If installing one of these frames, or if one has recently been installed, disregard the reinforcement, but install the linkage from the recall parts package. To begin the recall service procedure, operate the windshield wipers and cycle to the park position. Apply a section of masking tape on the windshield to mark the park position. Remove both wiper arms. Now, remove the nuts attaching the pivots to the windshield frame. At this point, remove the necessary hard or soft top components from the windshield frame to allow the frame to be folded forward. The next part of the service procedure is performed from within the passenger compartment. Disconnect the wiper motor drive link from the pivot link. Now, remove the 3 wiper motor mounting screws and remove the motor wiring clip from the base of the windshield frame. Next, remove the 4 inboard screws retaining the seal to the bottom of the windshield frame. These screws are removed to prevent the protruding screw ends from interfering with the pivot link assembly removal and installation. Now, remove the motor and drive link clear of the frame. Next, remove the C-clip retaining the drive link to the motor crank and remove the drive link. Do not remove the nut attaching the crank to the motor shaft. It's important to note this because removal of the crank is not required, and doing so will disturb the properly indexed crank position. Now, remove the pivot link assembly through the access hole on the left side of the windshield frame. At this point, check inside the windshield frame at the pivot areas. If the frame has recently been replaced, it may already have reinforcements, double metal thickness, at the pivot mounting areas. If so, the reinforcement in the recall parts package is not required. If no reinforcements are present, use a dry cloth to thoroughly clean the supplied reinforcement and the inner windshield frame at the pivot mounting areas. Thoroughly mix the two-part epoxy supplied in the parts package. This is accomplished by first removing the divider strip from the epoxy pouch. Using the rounded edge of the divider strip or any other suitable rounded edge tool, move the epoxy material back and forth in the pouch until the two parts are thoroughly mixed to a uniform green color. This should take about 5 minutes. Then move all the epoxy to one end of the pouch and replace the divider on the package. Use scissors to cut off a small corner of the pouch to dispense the epoxy. Apply a 1/8 inch bead of epoxy around both raised pivot bosses of the reinforcement and 2 beads about 2 inches long at the center. The center beads should each be about 1/4 inch wide. The reinforcement is now ready to be installed. Be careful during this stage of the procedure that you don't wipe off the epoxy while installing the reinforcement. Insert the reinforcement through the access hole in the windshield frame. Position it against the frame, aligning it with the mated pivot holes. The narrower portion of the end is towards the windshield glass. Make sure the reinforcement holes and notches line up with the windshield frame at both wiper pivot locations. Now, insert the pivot linkage supplied in the parts package through the access hole. This is done by turning the right-hand pivot towards the center of the link and feeding it into the access hole. The right pivot is the end of the link without the ball for the motor drive link. Continue to insert the pivot link with the left-hand pivot extended away from the center of the link. The left end contains the ball for the drive link connection. Install the pivots into the windshield frame holes, making sure the tabs on the pivots are lined up in the hole notches. This is done by rolling the pivots into the pivot holes with the left side pivot now turned inward or towards the center, and the right side extended away from the center. Now, raise the windshield frame and secure the pivots with the supplied nuts, tightening them to a torque of 7.5 foot-pounds. When installing the nuts, make sure the pivot tabs are positioned with the hole notches in the frame and reinforcement. Now, again, fold the windshield frame forward to rest on the hood. Use channel lock pliers to attach the drive link supplied in the parts package to the motor arm. Secure it in place using the previously removed C-clip. Use the channel lock pliers to attach the socket end of the drive link to the pivot link ball. Reposition the motor and secure it to the windshield frame. Install the motor wiring clip and the 4 inboard seal retaining screws at the base of the windshield frame. Spray a coating of silicone on the bottom of the seal surface. Now raise the windshield frame, being careful not to pinch the wiring. Finally, attach the frame and roof components as required to complete the service. Also, reattach both windshield wiper arms to the marked positions. For further information regarding affected vehicles, owners lists, and other service requirements, refer to the Dealer Notification Letter number 271T of March 1989.